So here's another example. Find the most general antiderivative of this function. So we can use the power rule. We can apply, we're going to first convert this to fractional powers. And then we apply that power rule in reverse. And we add, since we're supposed to find a general antiderivative, we add that arbitrary constant c. And you can verify that this is the antiderivative. And when we differentiate that, we're going to get lowercase f, the original problem. So we've seen by example that this is the way to find the antiderivative. This is the formula to use when you have a power function. And just like with the derivative law, the antiderivative of a sum is the sum of the antiderivatives. Multiplying by a constant is the same type of thing as with differentiation. And the antiderivative of a constant is, remember, that's like cx to the 0. So the antiderivative of a constant is just cx. So notice that in this table, this is the function, this is its antiderivative, and it's like you are reading it from right to left to find the derivatives. So notice there's a little bit of a problem when you have this power rule here, because when the power is -1, if you add 1 to that power, you get 0, and then you're supposed to divide by that, and you can't do that. So the exception to that power rule is we need to remember that the derivative of the natural log of x is 1 over x. And since finding the antiderivative is taking the derivative in reverse, we need to remember that when we see 1 over x, its antiderivative is the ln of x. However, there's another slight problem. The domain of the natural log of x, remember, is 0 to infinity. So that means that the domain, and since the domain of our original function 1 over x is all numbers except 0, we have to limit, we have to take care of that. So the antiderivative of 1 over x is the ln of the absolute value of x. So that takes care of that problem with the domain. And then, of course, we'll tack on our arbitrary constant for the general antiderivative. So here's another example to find the most general antiderivative, again, of this function. So we'll simplify it. And here we can apply what we just learned about the exponent being -1. And so we will find the antiderivative of 1 over t is ln of the absolute value of t. The antiderivative of 3 is just 3t. And the antiderivative of 6t to the -2nd is -6t to the -1st. So I'm adding 1 to that negative power and then dividing by it. And then I tack on that c. And notice the convention that the antiderivative is the capitalized letter of the given function. So there's some alternate wording. So notice that these examples, the examples had directions of find the most general antiderivative. So another way you'll see that is, find all functions h, in this case, such that h prime of theta equals 2 sine theta minus secant squared theta. So in other words, we're being given the derivative of a function. We need to find the antiderivative. So it's just being given to us in another form. So now we need to think in reverse again. We don't have a formula like the power rule. So what function's derivative is sine theta? Well, it's not cosine theta, because the derivative of cosine theta is minus sine theta. So the function that gives us sine theta would be minus cosine theta. Likewise, what function has a derivative of secant squared theta? Well, that's tangent theta. So therefore, my function is minus 2 cosine theta minus tangent theta. And since it said find all functions, that's again the general antiderivative, so I'm going to add that arbitrary constant c. So here is a table of formulas. It's hard to memorize these. I need to think of the derivative in reverse. So again, like reading this table from right to left, you're taking the derivative in that direction instead. So there's another type of problem you're going to see, and that's when you're asked to find a particular function or a particular antiderivative. So up to this point, we've been finding the general antiderivative where we have that arbitrary constant at the end. And but in this case, we're going to be asked for a particular unique function. So you need to be given another piece of information to find that one particular value for that constant c. So let's look at an example. So we had a previous example that we wanted to find the general antiderivative of this polynomial. And we found that it was this fourth degree polynomial, and we have that plus c. But now let's say we want to find a particular derivative. So we want to replace that c with an actual value. So we need to be given another piece of information. We need to be given another point on the graph, actually, so that when we plug the x value from that point in, we can solve for c. So we could say find the antiderivative whose initial value is 3 for this function. So we know the general antiderivative is this function, and then initial value of 3 means that f of 0 is 3, capital F of 0. So if we evaluate this function at 0, we solve for c, and this is the particular antiderivative. It's a unique function. It's not a family of functions like the general was.